session, the speaker is Professor Chen Ji, and this is also a second talk. Okay, please.
Okay, so good afternoon. Now let's start the second part of my lecture. So it's under this topic about halo nuclei clustering and universality. In the first parts, I will talk mainly about the general properties of halo nuclei. Now let's move to how it's connected with universality and use this framework called effective field theory to describe those universalities. And for the second part, let's focus on the two-body problems. So basically, one neutron halos, or maybe we can, in the end, we can extend it to proton halos. Maybe I need to click in the middle. Okay, now it's working. About the universalities, normally it's related to the properties that tells you it's independent of the details of the underlying interactions. So for the universality to exist, you need a separation of two different scales. In the coordinate space, it's related to the separation of short-range scale and the long-range scale. And in momentum space, this is related to a separation of low momentum scale with a high momentum scale. And we will talk about what those scales are related in the next slide. And if you have those separation of scales, then the physics you're describing, or the low energy observables, can be parameterized by a few parameters. And this is related, called universality, which means that many of those low energy observables are correlated with each other. So you need only a few parameters to determine their behavior. And with these universal behaviors, you can describe very different systems to show those identical or similar behaviors under those universal correlations. And now let's give a simple quantum mechanics picture of those universalities. So this is still a square well potential with a very short interactions. So the range of the interaction is determined by this L. And inside you have this attractive square well potentials, and outside you don't have any interactions with two particles at all. And if you calculate these two-body problems, you will find that its wave functions at large distances, this asymptotic behavior, is related to this A minus R parts. This A is actually related to the scattering length of the systems. So if it's positive, then it basically tells you how this potential will start in this part, right? And then you can relate the binding energies of this system to the scattering length. So the two-body binding energies is related to 1 over, there should be a bracket, so m times a square. So this actually shows you that this binding energy is actually independent of the details of the interactions. It's only parameterized by the scattering length. So you can put a black box at the short-range part of the interactions, and the physics at large distances is insensitive to the details at this short distances. What only matters is the boundary conditions. So you only need to match to these boundary conditions and put any potentials that can reproduce the same boundary conditions. You get the same long-range behaviors. And so you can study this large distance physics. It's based on this L over A expansion. So L is the range of the interaction, A is scattering length. And you can add more details of the interactions using perturbation series. So if those details of interaction matters, it will show up in this L over A expansions at higher orders. So you can use perturbation theory to include those higher order corrections or short-range information order by order into your low-energy observables. So this is why it's called universal behaviors. And actually, so under this universal physics, you can study the general properties of those low-energy systems or weakly bound systems in a model-independent way. So, and those few body low energy observables will show up as some universal scaling laws as functions of a few parameters. For two body parameters, the parameter can be the scattering length A, and if you go to three body systems, you have an additional parameters that, for example, you can parameterize as the binding energy of the ground states of the three body systems. And so basically, if you want to describe another observables, what you need to is write a universal correlation between the ratio of your observable with those parameters, two body parameters and three body parameters. So then you can, because it's insensitive to the details of your interactions, this will have some universal physics coming in different physics field. For example, it will show up in the nuclear halo systems we're describing in this school, and also it can be related to the ultra-cold atomic gases near the Feshbach resonances, because under this resonance you also have a really large scattering length. And it can also be related to some molecular systems. Also, for example, the helium dimer and trimer, which means if you have a cold atomic systems, the two heliums can form a bond state, and also three helium can form a very shallow bond state. So we'll talk a little bit about this in the next few slides. So this is some examples of those universal physics that observe in different systems. For those systems that will have this same feature, that its range of interactions is much smaller than its scattering length. So for the atomic systems, first you have these ultra-cold atomic gases, such as cesium-133, or the lithium gases, or this, I don't know how to pronounce this, it is with K39. And so for those systems, you tune a magnetic, first you trap those atoms in a magnetic trap or a optical trap. Then you vary the magnetic, you apply an external magnetic field to it, then you can generate this called Feshbach resonances. So the two atoms will generate a really large scattering length at a certain external magnetic field, but the range of the interaction, or the effective range, will keep at the small numbers. So in this way, if your magnetic field is close to, say, for this lithium-7 system at 740 G, so you will have a really large scattering length, either positive or negative, and a really small effective range. So this applies to these conditions. So then it shows some behavior as universal physics, and in tomorrow's talk I will mention some ephemeral physics related to that. And for these helium atoms, the range of interactions is basically a van der Waals interactions. So the range is determined by this van der Waals length, which is about 7a. So it's 10 to the minus 10 meters. And its scattering length is about 100A. So this has two orders of magnitude difference. So for those systems, they form this two-atom dimer and three-atom trimer states. And this trimer also have a shallow state related to ephemeral physics. So we'll mention that tomorrow. So basically, those are, you can use the universal features to describe those very different systems. And if you move to nuclear physics systems, and you will see that for those very light nuclei, such as triton, helium-3, and helium-4, the range of the interactions is determined by, for neutron proton, it's about 1.7 Fermi. So basically, like what Ingo said, it's determined by this pion exchange, right? By the pion exchange interactions. And the scattering length is related to the binding of the deuteron. So if you convert it into the scattering length, it's about 5.4 Fermi. So this is it's 1/3 difference. So you can also show, at a certain point, we can say that this is small and this is large. So you can describe universal features in those few nucleon systems. And Another example is what we want to talk about today is those halo nuclei, because we just mentioned in the morning that it has a tightly bound core with a few loosely bound valence nucleons surrounding it. So let's take helium-6 as an example. The core excitation energy is 20 MeV, so you need 20 MeV to excite the helium-4 to basically to break up into either proton and triton or neutron and helium-3. But the binding of the other two neutrons in helium-6 is only about 1 MeV. So if you convert this into a range, about this range, like an interaction range, is about 1.4 Fermi, and the distance which so it's basically tells you the size of the alpha particle, and the distance between the alpha and these two neutrons is about 3.7 Fermi. So this is also a separation of scales appear in halo systems. So you can see that for those those systems actually are at very different energy scales or distance scales, but they can describe by some similar universal features. Okay. So as we want to talk about the effective field theory and apply it to halo nuclei, let's first mention there was a discussion about what has been done for the theoretical study of halo nuclei, and there is a very nice paper by Alka Lilly called Halo Nuclei. It's a very small, a few pages of this small review. So he described this theoretical study of halo nuclei into three different phases. So that's called the first phase, the back to the envelope period. So starting from the discovery of halo nuclei to about 1990s. So basically, you use some quick estimates of the halo properties based on your measured reaction cross sections, and also this what we call the quick estimates is you use your normal knowledge about stable nuclei. For example, you can assume the nuclei still have a Gaussian spatial distributions. So then you will end up with a small reaction cross sections that generates a small matter radius. That can be hardly to explain what you observe for halo nuclei, which has a really large reaction cross sections. So actually, this part, actually, you find the problems that the old theory does not give you the picture of halo nuclei. Then from the 1990s to 2000, people start to use the field body method to models to describe halo nuclei. So you build those cluster structure models, and you describe halo nuclei as core plus valence nucleons. Then you can combine with field body reaction method to study those reactions for halo nuclei, including global model or DWBA or like CDCC method. So, because those field body models will have some interactions between the neutron and the core built by phenomenological method, so it has some unresolved model dependencies, similar to Ingo discussed about phenomenological potentials in nucleon-nucleon interactions. And this is not constructed systematically, so it has actually it has a limited predictive powers. So basically, you can describe some observables, but you don't know the uncertainty of your predictions. So this actually becomes a problem. And from the 2000 to now, people now use this microscopic models method, let's call it method, to describe those halo systems. This will be this ab initio structure series. So you have microscopic nucleon-nucleon interactions and 3 nucleon interactions with the many-body quantum method to calculate the properties of those halo nuclei. But it has difficulties in computational powers and extend to those physics at the threshold. I will show later in slides that because normally the traditional many-body methods are fitted for are very suitable for bound state problem calculations. But if you want to describe an observable near the threshold, basically the convergence is much smaller than those stable, the calculations for stable nuclei. So you need to combine with some other methods such as resonating group methods or Bergen basis method to implement with many-body mass calculations. And also nowadays we want to develop studies reactions also using ab initio series. So we need to want to develop this ab initio reaction series. Basically, use the build from the many-body Hamiltonians and to extract the optical potentials that can be used to describe nuclear reactions related to halo nuclei. But at the meantime, we can also describe halo nuclei with this effective field theory approach. And this approach, what is different from those approaching above is that it can systematically embed those microscopic information into the cluster model. So it's actually, I would say, it's a simplification to those ab initio calculations, but will combine with some advantage in the some simplicity in the field body models, and it can also provide a guidance to build reaction series. So I will talk about some how to build this effective field series in the next few slides. Okay, any questions up to now? Okay, if not, let's move on. So I think Ingo already mentioned gave a really nice introduction about Carrier effective field series. So I will show this plot again. This is a plot showing the different energy scales in nuclear systems, starting from QCD scales all the way to atomic nuclei, and also some rotational or vibrational states for nuclei. And you can see that for different energy scales, you can describe systems with different degrees of freedoms. So this is actually will give you an idea about the separation of scales. So if you focus on this atomic nucleus systems, then you can have a separation of high momentum scale and the low momentum scale, Q. This high momentum scale is lambda. So above this high momentum scale, you have the series, short range interactions, or even higher energy physics. So this is called the underlying series. For atomic nuclear systems, the underlying series is actually the QCD series, built upon the quark and gluon degrees of freedoms. And so now, if you look at the low momentum scale, the physics you're interested in is in this nucleon degrees freedom with pion exchange to describe its interactions. So we can actually, what people did with this argon V18 potential is to build a phenomenological series to describe their interactions. And on the other hand, nowadays we use this effective field series. Actually, it's combined this phenomenological way using these nucleon degrees of freedoms, but also embed inherit some of those symmetries from the underlying series. So from the QCD, so you can do a systematic expansions and to construct this interactions in this effective field series framework. And so this actually has an advantage that we can give you a predictive power. So you can, based on this systematic expansions, your theory will now have a controlled systematic uncertainty estimate. So, so we can see that the key elements for an effective field theory is this separation of low momentum scale and high momentum scales. And we already mentioned that this Q is related to the low energy observables, and lambda is related to underlying series, so basically short range interactions. And so now you have a systematic expansion of your Lagrangian based on this Q over lambda expansions. And you can do this order by order, construct your potentials. And so basically, if you go to higher orders, you will have higher powers in Q over lambda. And so if you truncate your expansion at certain orders, say, an order n, then the uncertainty of your predictions is controlled by the missing terms in your expansion. So terms at order q over lambda to the power n plus 1. So this will give you an estimate of the uncertainty of your calculations truncated at certain EFT orders. Okay, so then you can use this EFT to predict low energy physics, right? So because the low energy observables are insensitive to the details of the short range interactions, and you can basically at certain orders you can discover some universal correlations with this between low energy observables in your series. Okay, so let's take a few examples of those effective field series. One is, already mentioned, is Carrier effective field series. So to describe nuclear interactions in atomic nuclei, the underlying theory is QCD. So this high momentum scale lambda is about 1 GeV, so which would give you the quark and gluon degrees of freedoms. And if you are working in these pictures, then the interaction between two nucleons is described by these complicated pictures. You will have quark exchange and gluon exchange in the middle. So it's mimic the pion exchange in this way. And at low momentum, and this Q momentum scale is actually described by the binding per nucleon for atomic systems. So as we know that for stable nuclei, this binding per nucleon is almost 7 to 8 MeV. So if you convert this to a momentum scale, it's about 100 MeV. So this will give you the low momentum scale in your systems. And so if you forget about the QCD part and you just want to describe this low momentum scale physics, you can build a phenomenological potential to describe it. As Ingo already mentioned, there are many different models, such as the Bohm potential and also argon V18 potentials. And they will have, basically those potentials all have some repulsive cores. And the long range part is described by the pion exchange. But in the middle, you can have different series. For AV18 potentials, it's represented by 2 pion exchange, 3 pion exchanges, and so on. And for other potential, you have those sigma rho omega exchanges in the middles. So you can have different mechanisms for those interactions, and they will generate different behaviors at this middle range to short range part, and same behavior at the long range part. And but what do we know if those potentials are accurate? So nowadays you can combine these degrees, these nucleon degrees freedoms, and use QCD symmetries to build these chiral potentials. And just to mention that the chiral potential is not just a Z1 potential, because it can have some, let's say it's called this resolution scale dependence, right? So you have a cutoff in these potentials, and if you vary the cutoffs, your potential short distance behavior will change a lot. So you can see that its short range behavior, if you use different cutoffs, the short range part of this chiral forces would be very different. But what you also see is that the long range part of the chiral forces is almost the same. So let's remember from Ingo's talk that those potentials are used to describe nucleon scattering phase shift, right? So they can describe exactly the same nucleon scattering phase shifts, but in the interaction at this short range part is very different, which tells you that the nucleon scattering phase shifts at low energies are actually insensitive to the details of your short range interactions. It can be understood as a universal physics that's insensitive to short range parts of your interactions. And so now let's move from the chiral forces to a different field theory with only contact interactions. And so this is a theory called the Pionless effective field series. So it can be used to describe systems with very light nuclei. And we know that for very light nuclei, the binding energies or the the typical momentum in the system is lower than the pion mass. So you can look at this pion mass, pion exchange diagrams, and assuming that Q is much smaller than this the mass of the pion, then you can perform a Taylor expansions to truncate this pion exchange diagrams into different contact terms. So starting from a single constant contact terms with a term that has a Q-square dependencies. So this is actually how we build this interactions with only contact interactions, and this will work for physics at Q-square at the momentum smaller than the pion mass. And so it's actually very successful to describe observables in very light nuclei. And the plot on the left, it's shown. It's called the Phillips line. It shows the correlation between this neutron-deuteron scattering length with this triton binding energies. So the line is this dashed line is calculated using Pionless effective field series, and those small dots are calculated using different potential models. So you can see that if you vary those potential models, you get different numbers for those binding energies, but they are correlated in a single line, which can be described by the universal features. These universal features can be also described in Pionless effective field series. And on the plot on the right, it's called the tune line. It shows the correlation between a 3-body observables and a 4-body observables. Basically, you use different potential models to calculate these two quantities, the binding of triton and the binding of helium-4, and you will see that this number will vary a lot in potential model, but they are in the same, basically a linear line. So those two quantities are correlated by a single line. And this can also be explained by the Pionless effective field series. So the Pionless effective field series will help you to indicate that some universal correlations between different field body observables, and the long-range physics or the low-range physics is actually insensitive to the details of the short-range interactions. So this is demonstrated by these two pictures. And this Pionless effective field theory, normally our understanding is that it can only work with very light nuclei. But actually, recently people find it has another application areas is for this lattice simulated nuclei, because we know that in lattice QCD calculations, because of the computational resources limited, normally it's done at a finite lattice spacing, right? So under a finite lattice spacing, the pion mass is not the physical pion mass at 140 MeV. It's actually larger. For those calculations, the pion mass extracted from the lattice QCD calculations can be larger from 300 MeV all the way to 500 Let's see which one is pion. Oh, yeah. Yes, this is the pion mass, right? But this is the pion mass in the systems. But if you look at the binding per nucleon in these systems, it stays almost at, and it converted to the momentum scales, it stays almost at this 100 MeV levels. So this basically, it's insensitive to the lattice spacings. So you can see that at the real physics world, these two scales are very similar, right? It means that if you go to heavier systems, you have to have pion exchange degrees of freedom in your calculations. But if you work on this lattice simulated world, the pion mass is much heavier than the typical momentum scale for your systems. So you can just use Pionless field theory to describe those nuclei simulated in the lattice QCD, and this has been worked out by different groups and so on. We don't mention details here. So then another area is this halo nuclei, and we can see that the simplest halo is the deuteron, the proton plus a neutron. So we can call it either a proton halo or a neutron halo, depending on your taste, right? If you choose a left person or a right person. or this, you can also describe those neutron halos, proton halos, or alpha clusterings in this satisfy this separation of scales. And so for these halo systems, we also need to define its separation of scales. So these high momentum scales is related to the excitation of the core particles, right? And the low momentum scale is related to the separation of the valence nucleons in the systems. And so the underlying series above this high momentum scale is ab initio calculations based on nucleon-nucleon interactions and the many-body methods. And if you're at this low momentum scales, let's say, so, but if you, the difficulties of this ab initio series that because these absorbers are near the threshold, so you can also not just bound state, but you also have resonances near the threshold. The normal ab initio series has difficulties to describe those behavior near the threshold. So now you need to combine with continuum methods and also Bergen basis method, and also the like lattice effective field series. They would have some configuration trial wave functions and help you to set up these configurations. And also you have this Lorentz integral transform method to help you describe some continuum problems. And but there's another problem is the uncertainty control in chiral potentials. Because normally if you use these chiral forces, the target of the low momentum scale you want to describe is this, what we call this Q chiral effective field series at 100 MeV. And if you include higher order contributions, you will have corrections of the order Q over lambda from chiral effective field series at a certain powers, right? So this will give you the absolute errors for your calculations. But now remember that the physics you want to describe for those threshold behaviors at these halo scales. So the relative errors for your description of these halo scales is divided by these Q halos. And let's say this scale in the numerator is about 100 MeV, and suppose the neutron separation energy is about 1 MeV, you convert it into a momentum scale, it will be about 30 to 40 MeV. So this will be a factor of 3 to 4 compared to your normal chiral expansions. Basically means that if you calculate the binding energy of a stable nuclei, you get a certain uncertainty, a given uncertainty at the given chiral orders. But if you stay at the same order to want to describe the threshold physics, you'll find that your uncertainty is 3 or 4 times larger. So you must go to even higher orders to get a better accuracy for your predictions. Let's show an example. This is a calculation of this ab initio method with phenomenological potentials to calculate the nuclear spectrums for a wide range of light nuclei, and shows agreement with the experiments. But then if you compare this chiral effective field theory calculations using local shell model in the continuum to calculate the threshold physics, and you basically will see that if you use different interactions, your description of this threshold physics can change a lot. So which means it's very sensitive to this chiral interaction you're using. And so let's now we will talk about the difficulties in ab initio series. So one may ask that why don't we just use a simple cluster model to describe these problems? Because this already has this clustering pictures. But the problem is that with this clustering pictures, it's still a model, so it has a model dependence, and it's difficult to assign theoretical uncertainty to models. So a good way is to combine these two things. You can use the symmetries or information from chiral effective field series or ab initio methods, and also combine with these clustering configurations, so basically core plus valence nucleons degrees of freedom, to build your halo effective field series. The separation of scales is based on this Q over lambda expansions, will help you to construct your interaction in this halo effective field series. And the short range physics from the underlying theory will come in order by order based on these expansions, so it will come into some contact interactions. And for example, one example is the anti-symmetrization of the core nucleons and the valence nucleons, because in a cluster picture, you only have these two valence nucleons and the inner core, which means that the core is a single particles. But in the ab initio pictures, the core will have proton and neutrons. So if we do as anti-symmetrization, you also need to exchange the neutron, the valence neutrons, and the core neutrons, right? So, but this part is not explicitly included in this clustering pictures. But this type of information can be included in some contact interactions. So basically, you can put these informations into the halo effective field theory interactions. And so now let's build a Lagrangian to describe these neutron halos. So we start from a simple one neutron halos. It will have a one body Lagrangian and the two body Lagrangians. So the one body Lagrangians basically it's a two particle system. It has connected parts, connected term for this neutron, and also the connected term for the core particles. And for the two body interactions, you will have neutron core interactions, and it's more convenient. So for convenience, we also introduce a two-body dimer field. So it's a two-particle field for this neutron core states. And this delta is called the residual masses, which will give you like a Bell mass for this dimer field. And the mass, the total mass of this halo is called it's called this field the sigma field. So the mass of the field is m sigma. Sorry. And so because if you now the core can have some spin, because you can have a spinless core or a core with a spin. So if you combine this neutron and core, you also need to combine their spin, right? So couple their spin degrees of freedom. So you can use these operators, basically a Klapsch-Gorlin equations, a Klapsch-Gorlin coefficient to combine their spin into a given final state. So, and under this halo effective field theory, you can write the single particle field. This is similar to the Feynman diagrams, but for non-relativistic particles. So you have P0 minus its connected part. So if you use N and C is for the neutron field and the core field, and for this dimer field, if it's only a Bell dimers without interactions, then it's written in this form. So here it's the residual mass with this connected parts. But we know that for this Lagrangian, you also have interactions, right? So you also have neutron core coupled to this dimer field. So the true dimer interaction is addressed propagator. So it will have this loop corrections, which is called the self energies for the dimer field. So those dimer diagrams need to be, actually it happens at, so the first is a Bell dimers, then you have this neutron core, one loop self energies, and also it be repeated many different orders. But if you resum all those diagrams, so it's basically the resummation is like if you do a series in x plus x squared plus x to the cube, so you put this into 1 minus x, right? So this is like a series expansions. So this self energy will end up in the denominators of the additional contributions, and so then you can use this stress dimer field. So basically, you need to calculate self energies. So this is the equation. So it's related to this in the Feynman diagrams. It's related to this part. You have you have loop contributions. So in this loop, you have a single core and a single neutron. So you time this to get two fields together in this 4D integrals. So in the end, you will have a truncation, the momentum truncations. So include, this is like a sharp cutoff truncations. So you truncate your calculations at a certain momentum scale, lambdas. And if you do these calculations, you end up with analytic forms. So this part will depend on the momentum and energies of these self-energies minus this part is related to the cutoff scales. And so if you're working in the center of mass frame, so which basically means P, this capital P is zeros, and this energy then is related to only the relative momentum, K squared divided by its 2 times the reduced mass of these systems. So this, then if you sandwich this, you can then relate this dimer propagators to the two-body T matrices. And the T matrix can be written in this coefficient times K cotangent delta minus IK. So this delta is this S-wave phase shift. Ingo already mentioned this phase shift in his lecture. And if at low energies, this phase shift can you use the effective range expansions to parameterize into the scattering length and the effective range into these two terms. And so now let's work on this problem order by orders. We know that if you have a system with a very large scattering length, then R0 is much smaller than A. We can perform an expansion based of the T matrix based on this R over A expansions. So then at leading orders, you just drop these R0 terms. Your T matrix at leading order is parameterized by this A0 only. It's related to 1 over A0 plus IK to the power minus 1. So then you relate this T matrix back to the dimer form, the dimer propagators. So then you can determine the interaction coefficients in your for your Lagrangians. So at leading orders, so you have this W sigma equals zeros, and also the combination of the residual mass and the coupling coefficients will be related to A0 term. So it will cancel the cutoff dependence in the dimer field. And if you move to next to leading orders, this T matrix will have an additional term come from effective range corrections. So then you still match your coefficient to this A0 and also to this R0s. So then you will find that this W sigma will be related to the sign of this R0. So it's basically plus or minus 1. And also other two coefficients will be connected to this R0 and A0. So if you fit to experimental observables, you determine the coupling coefficients or the parameters in your Lagrangians. So after that, you can write this two-body T matrix as an order by order expansions. So now you have the T matrix in this leading order parts plus the next to leading parts as including a range corrections. So if you look at this form, you basically, we assume that the momentum scale of this two-body scattering is at 1 over A. So then your expansion obviously converges in this range. But actually, for this effective range expansion, it actually works better. It's working for even K times this interaction range. So K times R smaller than 1. So which means, and this interaction range is close to the effective range. So it has an even broader application range for the effective range expansions. And now this is for scattering problems. So if you want to work at one neutron halos, which is typically in a virtual state or a bound state, the binding energy is B is related to a binding momentum gamma zeros divided by 2 times the reduced mass. And so then you can determine this binding momentum related to scattering length and effective range. So in this formula, so if you know A0 and R0, you know what this gamma zero should be. So for this virtual or bound states, the two-body T matrix will have a singularity pole at K equals I gamma 0. So then you can instead of performing expansion in powers of k, you can perform an expansion around this pole positions. So you rewrite your T matrix around this pole. So you put 1 over A into this gamma 0 minus 2 R0 over 2 times gamma 0 square, and reconstructed this. Then you get this coefficient times this 1 over gamma 0 plus ik. So this will give you exactly where the pole of these two T matrices is at. And this coefficient actually is called the renormalization constant. And later on, we will tell you that this is related to the asymptotic normalization constant for the wave function. So now let's talk about T matrix, the pole of the T matrix, and how it's related to bound virtual and resonant states. So for halo or clustering states, and we can separate these states into 3 different categories. One is bound states. So if you look at the complex momentum plane, the pole of the T matrix will be an imaginary, will be on the imaginary axis of the K on the positive side. So basically above here, so it's a bound state pole. And if you have a virtual state, so you will have this pole is on the imaginary axis on the negative side. So this is a virtual. How do you separate virtual states and bound states? But if you have a resonant state, it always come with a pair of two poles, and we'll have a negative imaginary part plus and a symmetric real part, which means this one is negative and this one's positive, but they're mirrored along this imaginary axis. So you will have different states for different systems. For one neutron halos in S-wave, it's always show up as a shallow bound states or virtual states. But if you go to P-wave one neutron halos, you will have not only shallow bound states, but you can also have some resonant states coming in your halo physics pictures. Okay, so so how do we describe those wave functions for the S-wave bound states? So basically, let's see if I skip one slide. Okay, so basically to describe these S-wave wave functions, you need to calculate the Schrödinger equations, and on the right hand you have these eigenvalues, right? And we know that the T matrix can be solved in this Lippmann-Schwinger equations. So basically it's T equals V plus V G0T. And I think I will not give details about how to construct these equations. You can find this in the quantum mechanics textbook. And so basically if you rearrange it, put the second part on the right-hand side of the equation to the left, you will have 1 minus V G0 bracket times T equals V. So so then you can reconstruct these equations. For example, this 1 minus G0, let's see, 1 minus G0 term, we know that the G0 is the Green's function, can be written as this 1 over E minus H0s. So you can put this term together, put this 1 as E minus H0 times the Green's function, right? So this will be the one term minus V times E minus H0s. And you can combine the terms on the left-hand side. This will be E minus H0 minus V. So it's actually E minus H, the full Hamiltonian, times E minus H0s. So now the T matrix is written as this thing times T equals V, right? So then we can use the following relations that the V can be written as this equals V and equals E minus H0 minus E minus H. Okay, so then you can just do some multiplications on the left and on the right. I think I'll skip the details. You can basically, you can get to this line, the equation on this line. So basically here you just times 1 over E minus H on the left, and then also times 1 over E minus H0 on the right. So then you will simplify the thing on the right-hand side. You end up with these equations. So relate the full Green's function to this T matrix. And we know that for this T matrix, you can insert intermediate states in the middle. And if you're working at an energy that's very close to the bound state, then what the states really matters in the middle is the bound states wave functions. So this part can be written as E plus the binding energies of these two-body systems times in the numerators will be this wave function in momentum space squared, then plus some regular parts, because now this is based on the assumption that your energy is very close to this pole. So then the other part will be in this regular part. And so then we basically relate this 1 over E minus H to the wave function in momentum space. But then you can combine these two equations, right? So basically, it tells you that this 1 over E minus H has a pole as binding momentums, that's binding energies. But also on the right-hand side, the T matrix also has a pole as the binding energies. So we can then combine these two equations, then determine the wave function in the momentum space in this form. So it's written as a constant times square root of 4 over 4 times pi divided by k squared plus binding momentum squared. So if you do a Fourier transform, then in coordinate space written in this form with S wave, spherical harmonics part, and exponential tail part of the radial wave functions. And the coefficient in the front is what we call the asymptotic normalization coefficient. So it's related to square root of 2 times gamma 0 over 1 plus gamma 0 R0s. And the leading orders, you can drop these R0 terms, so they will give you the leading order A and C. And next to leading order, you have this correction of this 1 over square root of 1 minus gamma 0 times R0s. So the T matrix can be written in this new forms, some 2 pi over the reduced mass, and the numerator will depend on only the coefficients of leading order, the next to leading order A and C square over the leading order A and C square, and the numerator denominator is related to the pole of this system. Okay, so then we can use these formulas to basically calculate the A and C of this system. Because if you know the reflected range and the binding momentums, you can estimate this A and C. This will also help you to determine the expansion parameters in your system, because so this is basically related to R over A expansions. So its size can tell you how large the next to leading order contributions will be. And we can use these numbers determined from the experiments, the one neutron separation energy and the core excitation energy for different halo systems, and to estimate, firstly, this low momentum scale over the high momentum scale ratio. And also you can use the effective range over A0 to determine its expansion parameters. And also you can use A and C, right? So the ratio of the next leading order and leading order A and C will give you similar expansion parameters. Those are consistent with each others. So in fact, it's not always that you know R0 and A0 from the experiments, because sometimes you don't have the scattering data from the experiments. But on the other hand, the A and C can be determined from either experimental data or can be from an ab initio calculation, because you can use ab initio calculations to determine the wave functions and extract the asymptotic behavior of the wave functions. And this will help you to determine A and C. So you can use this thing to help you to determine the coefficients in your this expansion coefficients in in the halo effective field series. Okay. Okay, so any questions so far? Okay. Mm-hmm. I'm using a similar field as static Lyman field. Is there some difference or some reason in the outcome because it looks like the same algorithm? I think static dimer field means without these connected parts, right? Yeah, just this delta sigma term. Yeah. Right. So the thing is that at leading order, you really don't need this connected term. This only comes in at next to leading orders. So yeah. If you, I mean, I showed in the slides here. At leading order, this thing is 0. It's only related to the effective range, and this this W in front of this connected part can be either plus or minus, depends on the sign of the effective range. And if it's minus, well, it looks strange because for the single nucleon, single particle field, it's always plus, right? So it's actually, if it's a minus, it violates the causality, say. It will give you a state with a negative norm, which means it's unphysical. So it's called a ghost field. So it's a auxiliary field. It's not. It's just help you to build these two-body systems. And so, yeah. So if you stay, let's make it simple that if you stay at leading orders, you can drop these terms. So then you can still perform your calculations. Okay. So. No other question? Any other questions? Okay, now let's move on. Okay, so besides the calculations of the bound states or the binding energies, we can also calculate the structure of the one-neutron halos. So this is related to these electric form factors. So normally, if you want to describe the form factor, it's written in this called bright frame, which means that you have initial states, these two-body systems. In the center of mass of the center of mass motion of this system will have a momentum minus q/2. And then you have a photon inserted to the system. The photon will carry a momentum q. So in the end, the final state of this two-body system will have a total center mass momentum q/2. So basically, it's plus and minus for minus and plus for the initial and final state. The reason for why we do in this bright frame is that you want only the momentum parts. The photon only kicks in momentum into the systems, and it does not kick in the kinetic. It does not generate has a energy dependent energy part. So it's basically a spatial like form factors. And in this system, you will see that the center mass kinetic energy of the total center mass is unchanged after you kick in this photon field, right? So basically it's q²/4 divided by its 2 times its overall mass for the initial and final states. And so if you are at leading orders, you have only this the first figures where the photon couples to only this core particles, because the other particle is a neutron. It doesn't have a charge. The photon doesn't interact with these neutrons. So you will have these loop diagrams where the photons will come in coupled to the photons and then form into this bound state again. And so if you perform these calculations, you end up with these functions. And I think we can do an exercise later and then and talk about how to obtain these formulas. But if you go to next to leading orders, it will change this A and C parameters, and also you need to add an additional term as this photon couples to this dimer field itself. So this will help you with because if you look at this first term, if this C sigma, which is the A and C at leading order, is actually equals just to 2 times gamma. So at Q equals 0, this term will be just 1. So which means that your form factor is normalized at Q equals 0 is normalized to 1, right? This is the normal definition of form factors. But if you are at next to leading orders, this term will have this 1 over gamma 0 times R0 corrections. So if you put this in the Q equals 0 limits, this does not go to 1. So you need to have this additional term coming in to help you to fix the normalization conditions to put the form factor to be 1 at Q equals 0. So this is why it's important to have this additional term at next to leading orders. And this F is a ratio between the reduced mass divided by the total mass of the systems. So it's basically 1 over A plus 1. So now we can see that, as I already mentioned, that these two orders, the form factors are normalized to both orders. And we know that for the charge form factors, if you perform low momentum expansions, so it will be 1 minus this Q squared term, and this Q squared, the coefficient of this Q squared term is minus charge radius squared divided by 6. So this is well known, and basically you can verify this equation by assuming that the charge form factor is related to a Fourier transform of the charge density distribution in coordinate space. Then you can find these relations easily, and then if you use your these equations you derive from halo effective field theory for these charge form factors and perform this Q expansions, you will determine this rho C radius from your calculations. So this will be related to these factors. So basically mass factors and times this next to leading order over leading order A and C ratios divided by square root of 2 times gamma zeros. And this rho C is the radius defining the distance between the core particles to the center mass of this one neutron halo systems. Okay, so now we can use this formula and to check if we agree with experimental measurements. So basically from the experiments, you can either use, as I already mentioned in the lecture in the morning, that you can either use the matter radius or charge radius to determine this rho C in these two ways. So this will be given in the top panel of these tables where you have the numbers of this rho. So basically it's distance between the core and the neutron. So you have to time this A plus 1 factor in front of this rho C, get their average distance between the two particles. So then you can also use the analytic formula we calculated from the effective field series. If you know the binding momentum and the effective range, you will know how large this number is. And if you plug the number in, like what we did in this table, we will get this core neutron distances from the halo effective field series. You will see that for those two different systems, we show agreement between the experimentally measured measurements and the theoretical predictions. So this shows that the EFT has shown some universal features for different halo, this one neutron halo systems. Okay, so then besides the S-wave problems, we can also move to this P-wave problems, where you have neutron core interacting in a P-wave state. And so this will, for the P-wave interactions, you will have either enhanced shallow bound states or the resonance states. So for this P-wave interactions, we need to write the Lagrangian for neutron core interaction in P-wave. So this is written in these two terms, where the first term is still this dimer field for the P-wave to neutron core two-body particles, two-body fields. So it has a kinetic part plus this static residual part. and it has an interaction part. So this interaction will have a derivative in the middle, because now you have different from S-wave interactions. You have P-wave interactions, you will have additional momentum coming in. So for this field, it's written in this bracket for neutron core interactions, and this pi is the dimer field, and this derivative is actually defined in the center mass frame, so it's in a Galilean invariance form, where you have, it's basically to give you the relative momentum between these two particles. So then for the interactions, it's written as, because you also will have the combine the spin of the particles with this angular momentum related to these derivatives. So that's in this examples, we make it simple that assuming that the core is a spinless particles, so the core is spin zeros, and this applies to problems like beryllium 10 and helium 5, where for beryllium 11, the core is beryllium 10, right? So it's spin zeros, and for helium 5, the core is helium 4. It's also spin zero particles. So now, the core is spin zero, but the neutron have spin 1/2. So if you couple an angular momentum L equals 0 with spin 1/2, what's the final state we will have? It's a question, and anyone wants to answer it? Yeah, I can. Yeah, I'll offer a beer for the student who answered it. It's actually similar to what Ingo discussed. You have a spin and angular momentum, right? So if these two couples, so you get the total angular momentum J, right? So as we know in atomic physics, and this also happens in atomic physics, if you have a neutron has spin 1/2, and if interacting with the core in a p wave, L equals 1, and so you will have this spin 1/2 coupling with L equals 1. So this will split into two total angular momentum. One is J equals 1/2. The other one is J equals 3/2. So two different states. So basically, you will have two different p-wave interactions. We will give you two different p-wave dimer fields. And if you assuming that this p-wave, this J is either 1/2 or it's written here. It's 1/2 or 3/2. Then you can use this Klapsch-Gordon coefficient to couple this neutron spin with the angular momentum and generate this interaction operators. So now we have this general Lagrangians. So then the similar thing is that you solve this in this dress dimers in this picture. So it's very similar to the picture we saw before for S-wave, but the difference is that at this counter term between this dimer field and neutron core particles, at this part, you will have an additional momentum coming in. This is because this is where P wave enters. So the dress dimers can be written in this form. Here we simplify in the center mass frame, where you don't have the total P equals 0. So you have a residual part plus the energy part minus the self-energy part. And you can evaluate this self-energy parts into this loop integrals, where this is the single neutron field times the single core field. But different from the S-wave case, that because you have two momentum coming in at the vertex, right? One Q and another Q coming in from the left and from the right. So you have a Q squared coming in divided by 3. So this is basically like a 2L plus 1 in the denominators. So if you do this loop integrals, calculate these momentums. So I didn't mention before so this calculation actually can be, you can do this with mathematical. The first thing you need to do is separate this into a Q0 and the spatial momentum d3q, and the q0 you can use this Cauchy residue theorems to remove one of these single particle fields. So then it would be a 3D integrals for only one propagators, and it's actually you can get this analytic form. And if you don't want to do it by yourself, you can use Mathematica. It could easily help you to generate the final results. And so this is, you can see that this imaginary part would be I times k cube instead of I times k for the S-wave cases. And they also have two momentum dependencies. One is this depends on lambda times k square, and also a constant pieces depends on lambda to the power cube. So we need to match this dress dimer propagators to the p-wave T matrices, and we know that for the T matrices, if you use the effective range expansion, it can be written in the form on the left. So it's basically k square cosine theta, which means that you have an incoming wave, incoming momentum, and outgoing momentum. The magnitude of this k and k prime are the same, but they can be at different angles. So the angle is defined by just theta. And so in the denominators, you have this p-wave scattering volume, which is in the dimension of L to the cube, and also have this p-wave effect range minus 1/2 times R1 times k square. And for this p-wave interactions, this p-wave effective range is actually not in the scale of L. It's not in the dimension of distance. It's actually in the dimension of momentum, right? So so then you will see that these two match with the same dimensions. And the last term is called the unitary term, is I times k to the cube. And so an interesting feature for the p-wave interaction is that it does not have a well-defined unitary limit. We know that for S-wave, you can put this A to infinity and put R0 to 0, right? So it's called zero range interactions. But for the p-wave, you cannot do that. It was proven by Nishida and others that for the p-wave, this R1 is always smaller than 0, and this R1 must not go to 0. If this go to zeros, your wave function will have a negative norm, which means it violates the causality conditions. Its probability is smaller than 1, so it's not possible. So actually for p-wave you don't have a unitary limit, which means that you need both of this A1 and R1 at leading order for p-wave interactions. For S-wave, we already see that for S-wave, A0 appears at leading order and R0 appears at next to leading orders. But for p-wave, it's different. Both parameters need to appear at leading orders. And there are discussions about the power countings for p-wave interactions. We were started by these two papers, and the first one by Bertonari, Hammer, and Van Kalk, and they argue that for p-wave interactions, and A1 is of the order q to the power 3 of q to the power minus 3, and R1 is to the power of q. So both are related to the soft scale. And for this power countings, you can generate a broad resonance or a shallow bound states. And there are different power countings was discussed by Bidaki, Hammer, and Van Kalk in the following papers. So they assume that this scattering volume is in the power of 1 over halo scale q squared times lambda, and R1 is related to the high momentum scale, related to the power to the lambda. So for this power countings, it will generate a narrow resonance state. So it will describe different p-wave systems. So let's talk about what's the consequences of using these different power countings. So if you use the power counting by Bertonari, Hammer, and Van Kalk, where A1 is of the order Q to the -3, R1 is of the order Q. So you can draw the picture of the position of the pole for these T matrices. You will find that you will have a low energy bound state pole plus a resonant pole. So this two resonance poles coming together. So for this case, the binding momentum is of the order Q, and both the position of this resonance is Kr and its width are both at the order of Q. So it's a broad resonance, which means that its width is in the same order as the position. So it's if you draw in the consider it's a Wigner resonances, it's quite extended, the position and the width are in the same orders. So this is so basically you expand this, right? You expand this denominators into this three, factorize into these three parts. The last two comes with this paired resonance poles, and the first one will give you the bound state poles. So so this can help you to describe some of those p-wave states that has a bound state. And there are the different power counting is by Bidaki et al. And so they argue that A1 is of the order 1 over Q squared times lambda, R1 is of the order lambdas. So for this power counting, so based on what we know for Q over lambda is approximately about to the 4, I think this number is coming from helium-5, and this is 0.15. And if you go to different systems, they can move to say 1/3. So basically means that you need one fine tuning and one natural tuning at leading orders. So for helium-5, take helium-5 as the example. So it has this three half minor states will have a p-wave resonances, which means that A1 is smaller than 0. So in this complex momentum plane, it generates three poles. We said that it generates a bounce. It can also generate a bounce state pole, but the position of this bounce state pole is very high on the imaginary axis. So which means that it's a deep bounce state pole, and it also generates a shallow bounce state pole. But the width related to that, it's one order smaller than its positions. So it's a narrow resonance pole. At leading orders, because we know that for helium-5, we only observe this shallow resonance, but we don't observe these deep bound states in helium-5s. So actually, at leading orders, you can use these power countings and find that this imaginary part is one order smaller than the other two pieces. So if you drop these pieces, you will end up with a resonance pole, but with 0 width. So this basically means that these two poles move to the real axis, and the bound state pole will push to infinities. So it goes beyond your application range. So you can just exclude this bound state pole at leading order. So, but the fee you need to pay by doing that is that you can only describe this T matrix at a certain range of this momentum. Basically, you can describe for when k squared is smaller than 0, which is applicable for when you are using this effective field theory to describe helium-6, because helium-6 is the bounce systems. But if you want to describe a resonance positions, once your k squared is, once your energy is near the resonant poles, then this imaginary part will be important. It cannot be dropped. For example, if you want to describe the resonance in helium-6, then you also need to include this unitary term. So we can make a comparison of these two the power countings for helium-5, and we can extract its scattering volume and effective range based on the phase shift analysis. So and also you will find that it has this 1/2 plus states. It has a S-wave scattering that enters at next to leading orders. So If you use this power countings based on the Bidaki et al. And treat this IK cube term as next leading orders, you will find that you can describe well the phase shift or the scattering cross sections at low energies. But once you move close to the resonances, this power counting doesn't work well. So this is shown by the dashed line here, the dark dashed line here. But if you use this power countings by Bertrandani et al., well, this unitary term is always treated in the denominators, then you can well describe these resonance positions, both as leading orders and next to leading orders. But the problem is that for these power countings, you, as I mentioned before, that you will generate shadow bound states in your systems. So if you want to calculate, for example, helium-6, you need some techniques to remove this shadow bound states. And one way of doing that is using this technique called Pauli covalent state projections. Since I'm only talking about two-body problem here, I will not mention details about those techniques in this lecture. Okay, now let's move on. Now let's take some examples of these P-wave bound states. And the first example is beryllium 11. So it has both a S-wave bound state and P-wave bound state. And for this P-wave bound state, we know its one neutron separation energy is very low at 180 keV. And you can also use scattering phase shift to extract its scattering volume and effective range. So you can use these numbers to get its binding momentum for the P-wave binding momentum, and from these formulas. So you know scattering volume and effective range. So you use this to construct gamma 1. And so then you can use this to get expand the T matrix around the pole positions. So you will end up with this formula, a coefficient times this energy poles is E plus B1 in the denominators. And very similar to the S-wave case, you can also write this 1 over E minus H and expand it around the pole positions. So it's related to the P-wave wave function at the momentum in the momentum space. So if you compare these two equations, use the formula we discussed for the S-wave, you can obtain this wave function in momentum space written in this form. So it will be similar. So it's a coefficient times k squared plus gamma 1 squared. But different from the S-wave case is that you have additional powers of k in the numerators. And so then the thing is that if you still want to get the wave function in coordinate space, you need to do a Fourier transform of these wave functions. So you end up with this form in coordinate space. So the different part is that it has this thing in the brackets from the S-wave. And asymptotic normalization coefficient is also different from the S-wave. So now it depends on gamma 1 and R1 in this form. And you also, if in the case that if you use this Bidaki power countings that R1 is one order higher than is in the high momentum scale and gamma 1 is in low momentum scale, you can do a perturbative expansion of these A and C parameters, getting the leading order part and the ratio for the next leading order part. Okay, so I hope it's clear up to here. And any questions? Okay, so now let's move on. And so with the wave functions, you can calculate the root mean square radius between the core and the neutrons, use these simple formulas, right? So this is understandable. And so if you do these calculations, I don't think it's not needed for us to discuss about the details of how to do integrals. You can use Mathematica to help you to perform this, or you just put this into say GPT. It can help you to get the answer and also show you the derivation. I tried that; it actually works. So, so now let's move to some different problems that relate to the Coulomb dissociation in one neutron halos. And this Coulomb dissociation process, as we mentioned in the morning, that you have a heavy target that has a highly charged particles. So the halo will come in that will have feel these Coulomb excitations, and because it's a strong electromagnetic field, so then the nucleus will be excited. It can break up into different pieces. If you stay at low transfer momentums, then it's related to the physics of these halo pictures. So then we can use effective field theory to describe this low momentum part of this Coulomb dissociations. So the dominant part is this electric dipole transitions. And so basically, for S waves, if you don't include any P wave part interactions, then it's written in these two diagrams. The first diagram is that the photon couples to the core particles, then directly break up this bound state into the continuum states. And the second picture will comes in at next to leading orders. This will give you an additional final state interactions, which means that the photon comes in, interact with the core field, and then the core and the neutron will then interact again at this point, and then it will generate additional contributions to this E1 transitions. So basically, you can write this in this form. This coefficient is related to the normalization constant of this T matrix, and this part is related to the plane wave of this single particles after the continuum states. So this will give you the matrix elements for these problems, and so then you want to extract the electric dipole contributions of this matrix. So you need to do a linear expansion of this denominator. So basically, these two have that angles, and you put this Q in on the z-axis. So then divide by this functions Q times this spherical harmonics y10 and put Q at the z-axis. This would be a constant number times Q. So then you divide this, you get this matrix element for transition from the S wave state to a P wave state to a P wave continuum state. So this will end up with this matrix elements for E1 transitions. And so then, as we mentioned at the beginning, that if you have an L equals 1 final state, because the neutron has spin 1/2, when these two couples, it will generate into either J equals 1/2 and J equals 3/2. And these two will both contribute to this E1 transitions. So you can use this spin orbit couplings to relate this spinless E1 transitions to the one with J equals 1/2 and 3/2. And this prefactors actually comes from the Collapse-Gordon coefficients. So you get this matrix elements related to these two J states. So then, if you want to calculate the differential E1 strengths, transition strengths, you need to calculate this matrix elements squared and put it together times D3P divided by DE. So after the evaluation, you end with this final formula related to the ANC coefficients and the transfer momentum divided by binding momentum squared times this transfer momentum squared to the total to the power of 4. And so the thing is that this formula actually will show some universal features. Because if you put this momentum scale into the energy scales, it can be written as transfer energy divided by the one neutron separation energies. And you can define this Q effective, which means a coefficient is 1/A+1 times the charge number of the core particles or the halo part of the one neutron halos. Then this dBE1/dE can be written in this new forms, and it has a coefficient, constant coefficient, times this E minus S1 neutron ratio as the functions. So it's basically it turns into a scaling functions as we mentioned at the very beginning, that these universal features are always comes with the scaling functions. Your observables can be always written as the ratio between an energy and some given energy scales, for example, the binding energies. So then you can, what we see is that this will show up as scaling functions, and the only part that's the system dependent is those coefficients in the red, in the blue, and also I didn't put is the A and C coefficients are also system dependent. So if you move from, say, one halo system to the other one, the rest part is the same. This power law behavior is same for different one-neutron halos. What is only different is the prefactors. So we can also calculate this non-energy weighted sum rules for dBdE, and then you end up finding that it's actually, you can write this related to this core neutron radius square. So just verify what we talked about in the morning lectures. This this total strength of the UN transition is related to this this core radius squared in these halo pictures. So we can use this to calculate the E1 transition for deuterons, and this shows this scaling behaviors. So as we mentioned that it has an additional this prefactors will give you some system dependent parts, and if you multiply this to your dBdE, you have universal functions. So then, if you plot these universal functions and compare with the data for E1 transition in deuteron, they actually match very well with each other. This is also because the deuteron is a simple system. It doesn't, the neutron and core it basically doesn't have other structure inside it, right? Because it has large separation and energy scales. But if you move to systems such as beryllium-11 and carbon-19, what is measured is this Coulomb dissociation cross-sections. So it's related to the E1 strength with additional terms that is called the total virtual photon numbers related to the impact parameters R, and also it's describing the strength of the electromagnetic interactions for different systems or for different experimental setups. And these factors can be calculated analytically. Basically, you just need to know the photon energies and the impact parameters, and then you can use some analytic form to get these numbers. So this was shown in the paper by Bertronari, that they plotted this this virtual photon numbers as a function of E gamma at some analytic form. So then we can then rescale this differential cross sections to the universal functions. You just need to time these prefactors in blue to the two sides of these equations. So then the thing on the on the right hand side would be a universal functions. So you can put the measured carbon-19 differential cross section and beryllium-11 differential cross sections rescaled in the same plot, and the line the solid line is for the universal function for carbon-19, and the dashed line is for beryllium-11. The small differences is coming from this total virtual photon numbers, so it will generate small variation to these two. And we see that after doing that, the experimental data for the carbon-19 Coulomb dissociation cross-section match quite well with the leading order, or not leading order, the universal curve for this E1 transitions. But for beryllium-11s, the data is below this curve. So what's the reason for beryllium-11? The disagreement between the theory and the experiment is that for beryllium-11, it has a p-wave bound states. So in the calculations, what we did is we only calculate the S wave directly break up into the continuums. But if you have the S wave with the Coulomb excitation to the P waves, it can have some cancellations to this E1 strands, so it will move this line down. It can possibly move this line down to closer to this data points. Okay, so that's a discussion about one neutron halos. And any questions? I think I only have a couple of slides after that. Yeah, it's okay. A few more slides, yeah, a couple more. So up to now, we only talk about neutron halos without Coulomb interactions. But we know that for those nuclear systems, we also have proton halos or alpha-alpha systems. So this is an example of how to describe halo using halo effect field theory with Coulomb interactions to describe proton halos. So what's the difference is that for this core neutron interaction, you not only have strong interactions, but it's also the core and neutron has the long-range Coulomb interactions coming in. So the Coulomb interactions need to be summed in these loop diagrams. And so basically what's changed in this Lippmann-Schwinger equation is that the Green's function is a Coulomb Green's function. So you need to, your inserted basis is not plane wave basis, but Coulomb wave function basis. And the Coulomb wave function is known in the literatures. So after doing that, you can still solve Lippmann-Schwinger equations and then get the T matrix for, say, PP scattering and also P alpha and alpha alpha scatterings. And this has been also applied to study the excited states of fluorine 17. And so if the Coulomb momentum is smaller than the typical momentum of your systems related to the proton separation energies, then you can treat the Coulomb perturbatively. This has been done by Sebastian Koenig and his collaborators to study Triton and helium-3 using these perturbative Coulomb expansions. And so I think I will not talk about too much details about this. And so then you can also study electromagnetic interaction reactions related to neutron or proton halos. So the basic picture is that you have, so this is a radioactive nuclear capture processes. So basically you have, so for neutron captures, you have this neutron coupled with these core particles, then emit a photon out and form a bound state. It also have a final state interactions at higher orders. And for proton halos, it's a bit different because you have the final state will have long-range Coulomb interactions, so it will always have a Coulomb, asymptotic Coulomb wave function for the final state. And so, and this has been applied to many different systems. So I just put this references, several references, if you're interested in, and I won't talk about details here. So this has been applied to study this radioactive neutron capture, this proton capture for beryllium 7, and to get to the boron 8. So this, and then this can be used to extract the astrophysical S factors. So it was done by Shilin Zhang and Ken Norris and Daniel Phillips, and they used this halo effect field theory method to extract the S factors for the astrophysical reactions, and then so you can combine this with Bayesian analysis to get the uncertainty estimate for their calculations, and it has actually works quite well for these systems and give you a quite accurate S factors at very low energies. And the issue is, I think that the key important part of this calculation is that in the experiments, because the proton and the beryllium 11 will have a Coulomb repulsion between each other. So normally when you do experiment, you cannot go to very low transfer momentums. So you always need to do extrapolations. But halo effective field theory will help you to give you a physics guide on how to do these extrapolations. based on the physics, because in the effective field theory, you can well describe the low energy part. So you can extend it to the intermediate range, and also use the Bayesian methods. You can combine the uncertainty from the experiment to help you to get the uncertainty as the zero energy as factors. Okay, so I think this is all the slides I want to discuss here. And any other questions?
Okay, in any case, thank you very much for the nice talk. Okay, so do you have any question? Okay, over there.
Hello, I have a question concerning the renormalization of the theory. So this is basically very similar to Pionless effective field theory, right?
Right.
And in Pionless effective field theory, you also get these two-body currents when you have E1 processes. Do you get anything similar for normalization group arguments in Halo EFT?
Yes. Well, you can. Well, since in these problems we have this dimer field, right? So some of these two-body currents is represented by the photon coupling with the dimers, and so I showed the picture. Let's see. Wait. Oh, S-wave, right? Showed in that. Yeah, this part. Yeah, this is an additional picture. So this basically photon coupling with the two-body field. So this can be considered this two-body current. Okay. And so if you use a Pionless effective field theory with contact interactions without this dimer field, at leading order the interaction is only C0, right? So if you do the gauge transformation, the photon coupling only comes from the connected part, single particle connected parts. And where does this two nucleon current comes in is once you go to next leading order, you have C2 times Q squared terms. Then this Q squared term, you put this second order derivative into covariant derivatives, you generate two-body interactions. And this is similar because as I showed the Lagrangian that at leading orders, this dimer field only has a static part. It only depends on the residual mass. And this part does not have any derivatives. But once you have next leading orders, you have this delta square and partial zero coming in. So if you change its covariant derivatives, you have this photon coupled with this dimer fields and next leading order.
Okay, you also showed results for the deuteron, right? So in the deuteron, you usually fit the LEC of this two-body current to the thermal neutron capture cross-section. But as far as I understand, for you, this is the LEC of this two-body current is already given by theory?
Two-body currents, for which system can you mention again? Deuteron.
I think you showed some
so
E1
for this
results
one,
for the deuteron.
yeah, this one is only I think for this U1 transitions, we don't need to include two-body currents at this order. I think it comes at yeah, it should, for U1 transition, it comes at higher orders.
Okay, thank you.
But the two-body currents for, I mean, I studied the different systems. Actually, for the convection currents, the E1 transition is related to the charge operators. But if you look at the convection currents at higher order, and next to linear order, you have a two-body current. And for the magnetic operators, you also have some two-body currents coming in.
Yes, I meant in the context of NP to the gamma, for example, this is,
okay.
You actually need this to get agreement with data, right? And you also showed some results for the deuteron, which is what,
yeah.
what I meant.
So, but for this next to linear order calculations, the only change is the A and C. So, yeah, I think cannot remember where. Yeah, that probably doesn't come in for this part.
Okay, thank you.
So
Anyway,
any
we
other?
can soon have a discussion section.
Yeah.
We can go deeper.
Okay, so in any case, do you have any short question? If not, okay, here.
I've got a question about so Coulomb dissociation within the Halo EFT. So with the picture you show like the DB1DE and saying that the curve was below
Yeah,
because there was a P contribution that was missing.
right.
So basically, so when you show all these results like these universal function, that's without final state interaction, right?
Well, it's with S-wave final state interactions.
Oh,
So you can see the picture that,
yeah, but here, like
yeah,
if the
this pictures.
yeah, so
So
there is S wave.
This
like
part
on
is the final state interactions.
Okay,
right?
okay,
So,
okay,
so
okay,
you
okay,
have
okay.
a S-wave final state interaction
Yeah,
coming
yeah.
in, and next to leading orders.
But like, it does not play any role if the ground state is like positive parallel state, right? Because
It
you do
doesn't,
like,
but it change. I think it comes to this this
okay,
part.
okay,
yeah.
for that part.
Yeah.
And then I had another short question that was for the when you show like the Bertolani power counting versus like the Bedak,
Beta
like
power
the other
counting,
one.
yes.
I did not understand like where does that come from? That in the Bertolani case, I think it was like slide 31, that you said something about like the width is broad.
Yeah.
the resonance or
So
shot.
basically, you need to expand this. So it's a it's a it's an equation with so this has a k
Yeah,
square, a k
yeah.
cube, k square. So you can factorize into these three parts, right? So basically, three roots for this denominators.
But the statement of like when you said like the width is of all
Right.
the
So
Q,
this part, this is imaginary. So this is
Yeah.
a pole in
Yeah,
on the
yeah.
imaginary axis, and those kappa minus and kappa plus are complex numbers.
Yeah.
Will give you this these two poles. And if you I didn't show the formulas, but if you look at how these points are related to R0 and R1 and A1, and if you put A1 and R1 both for using this power counting, so related to Q, then you find that both the position and gamma is related to the powers of Q, not to the powers of lambda. Well, this is natural because here, if both those parameters are in powers of Q, then everything is related to the powers of Q, right? No, nothing is related to the high momentum scale. So it's always related to soft scales.
Okay, another question? Okay, so if not, let's close this session. Thank you very much for the nice talk. Okay, so we have a
It's the
break.
coffee break here. Let us delay a little bit and come back 3:45, okay? Then we have about 30 minutes of rest.
Okay, so from
Okay.
now we have 30 minutes,
And
and
then
break.
we start the discussion session.
Okay, yes.